Welcome back, guys. In this teaching video, I'm looking at part 3 of 7.4 static of rigid bodies. So I'm going to be covering two examination style questions. So we're studying equilibrium of rigid bodies. Two conditions are satisfied. The sum of clockwise moment is equal to the sum of anti-clockwise moment. Resultant force horizontally or vertically is 0. Now to calculate the moment of a force, we apply the formula force multiplied by the perpendicular distance. For simplicity, we are going to consider the horizontal and vertical forces only. Here is exam style question 1. A uniform rod AB of weight W and length 8A rests in equilibrium with the end A on rough horizontal ground. The rod rests on a smooth cylinder, as you can see over here. The distance A to C is 7A. Part A, show that the normal reaction of the ground on the rod at A has magnitude W in bracket 1 minus 4/7 cos squared alpha. Part B, the coefficient of friction between the rod and the ground is mu and cos alpha is equal to 3 over square root 10. Find the range of possible values of mu. So I'm going to start by going through the solutions of part A. The very first step is to label the distances and forces in this particular diagram. So what we have is that the rod is uniform. The weight acts at the center, so we can label that weight as W. W is going to split the distance 8A into two equal parts. 8A divided by 2 is 4A. So we have 4A. The distance A to C is given as 7A. So we know that this portion over here, therefore, has to be 3A. So 4A plus 3A is 7A. The whole distance A to B is 8A. So 7A is used up. The remaining amount is A. So that part there is A. Okay, now this rod is resting on the cylinder. So there will be a normal reaction coming out at the point C. We can call this normal reaction RC. Now, at the point A, we have a rough horizontal ground. So there will be a normal reaction coming out of A. We can label it as RA. And if this particular rod was to slip, it will slip to the left, and so friction will act to the right. That friction, I'm going to label it as FA. For this particular force, we can actually form the horizontal and vertical component, form a right angle triangle. So here is my right angle triangle. Okay, it can be shown that this particular angle is also alpha. But the proof of this is not necessary. Anyways, I can now put in my arrows. This is the adjacent, so this force would be RC cos alpha. This is the opposite, so this force would be RC sin alpha. Okay, so that's all the distances and the forces labeled. Remember, for simplicity, we are only considering the horizontal and vertical forces. Now in part A, we want to show that the normal reaction of the ground on the rod at A has magnitude given by this expression. So what are we trying to calculate? Well, we're trying to calculate the value of RA. And that value will give it as an expression, which will be this one here. Okay, so our target for part A, ladies and gents, is to work out RA. First of all, equilibrium implies that two conditions are satisfied. The first one, sum of clockwise moment, is equal to sum of anti-clockwise moment. And condition number 2, resultant force horizontally or vertically is 0. These two conditions are satisfied. Now to work out RA, I need to resolve in the vertical direction because RA acts in the vertical direction. So I'm going to be resolving vertically, taking upwards to be the positive direction. We know that the resultant force vertically is equal to 0. So what is this resultant force? Well, it will just be RA plus RC cos alpha minus W, the weight. of the rod equal to 0. So RA is equal to W minus RC cos alpha. So if I go back to my desired form, there is no RC involved. So I need to eliminate RC. So now I'm going to work out RC. What is RC equal to? Right. To do this, I can go back to my conditions. The first condition says sum of clockwise moment is equal to sum of anti-clockwise moment. If I take moments about the point A, all the forces coming out of A are now neglected, the FA and the RA. That will help me calculate the RC. So I'm going to take moments about A to calculate RC. Sum of clockwise moments is equal to sum of anti-clockwise moment. So if I hold my pen at the point A, this weight W will take the whole body clockwise. This normal reaction RC will take the whole body anti-clockwise. Let's start off with the clockwise moments. I'm going to form a triangle. So I can stretch out that weight downwards and then form a right angle triangle. Okay, this part of here, the angle is alpha. Now the distance from A to that weight is 4A. That 4A is not the perpendicular distance to the force. The perpendicular distance to the force W will be this component over here, which is the adjacent. It will be 4A cos alpha equal. Let's have a look at the anti-clockwise moment. So RC will take the whole body anti-clockwise. So we've got the force RC. And from A to C, we've got the perpendicular distance, that is 7A. Okay? And that there completes my diagram for the clockwise and the anti-clockwise moment. Now I'm going to calculate the moment of each of these forces. Let's start off with this one over here, ladies and gents. The moment of that W force will be W multiplied by the perpendicular distance, 4A cos alpha. This must equal to the moment of the RC force, which is RC multiplied by 7A. Or 7A multiplied by RC. So we have 4A cos alpha W is equal to 7A RC. Notice that we have a cancellation here. The A's cancel. So we have 4 cos alpha W is equal to 7RC. Making RC the subject gives us RC is equal to 4 over 7 cos alpha W. Okay, now if I come back over here, I can call this equation 1. And then if I go back here, I can call this equation 2. We can now substitute equation 2 into equation 1. So if I substitute equation 2 into 1, I get the following result. RA is equal to W, so we have W minus RC, which is this one over here, 4 over 7 cos alpha W multiplied by cos alpha. So that there, ladies and gents, gives us the following result. RA equal W minus 4 over 7 cos squared alpha W. So at this stage, we notice that there's a common factor of W. We can take out the W, giving us RA equal W in bracket 1 minus 4 over 7 cos squared alpha. And that's exactly what I needed. Right, so now we can move on to part B. The coefficient of friction between the rod and the ground is mu, and cos alpha is equal to 3 over square root 10. Find the range of possible values of mu. Because it's the range of possible values of mu, our answer will be in inequality form. Now cos alpha equal 3 over square root 10, that there is very important to us. We're going to construct a right angle triangle in order to work out the value of sine alpha and tan alpha. So here is my right angle triangle. So what we have here is that cos alpha is equal to 3 over square root 10, adjacent over hypotenuse. So the adjacent is 3 and the hypotenuse is square root 10. If we use Pythagoras theorem, the opposite would be 1. So from this triangle, we have that sine alpha is equal to opposite over hypotenuse, so 1 over square root 10, and tan alpha is equal to opposite over adjacent, so 1 over 3. Now, we want to find the range of possible values of mu. How do we do this? Well, first of all, we know that the rod is in equilibrium. This implies that Fa, the friction at A, is less than or equal to F max, the maximum friction at A. We're going to be using this particular result in order to work out the range of possible values of mu. I'm just going to clear the board, okay? Okay, so we've got part B. We know that Fa is less than or equal to F max, the maximum friction at A. So Fa has to be less than or equal to mu multiplied by Ra. Now we know what Ra is, ladies and gents. We've got Ra, it's over here. So we have that Fa is less than or equal to mu multiplied by W in bracket 1 minus 4 over 7 cos squared alpha. Our target is to work out Fa. Once we get Fa, we can rearrange and make mu the subject. So how do we work out Fa? We are going to resolve horizontally. So resolve horizontally, taking right to be the positive direction. Horizontally, the resultant force F is equal to 0. So what will that resultant force be horizontally if we take right to be the positive direction? Well, it will be Fa minus Rc sine alpha. So that's the resultant force horizontally. This must equal 0. So Fa is equal to Rc sine alpha. But Rc was equal to 4 over 7 cos alpha W, which means that Fa is equal to 4 over 7 cos alpha W multiplied by sine alpha. Hence, Fa is equal to 4 over 7 sine alpha cos alpha W. Okay, so we've got Fa. Now, if I come back over here, I can call this inequality 1, and this one over here, we can call it equation 2. So we're going to substitute 2 into 1. Substitute 2 into 1. Right, so if we do this, we have Fa, which is this over here, 4 over 7 sine alpha cos alpha W is less than or equal to mu W in bracket 1 minus 4 over 7 cos squared alpha. So over here we notice a cancellation. The W's cancel out. This reduces the inequality to 4 over 7 sine alpha cos alpha is less than or equal to mu lots of this bracket cos squared alpha. Now we know what sine alpha is, and we know what tan alpha is, and we also know what cos alpha is. But if we go back to this inequality, we are only interested in the exact values of sine alpha and cos alpha. So we can substitute sine alpha equal to 1 over square root 10 and cos alpha equal to 3 over square root 10 into this inequality. So if we do this, we end up with 12 over 70 is less than or equal to 34 over 70 mu. You can rewrite it as 34 over 70 mu is greater than or equal to 12 over 70. If we multiply both sides by 70, they cancel out. So 34 mu is greater than or equal to 12. Hence, mu is greater than or equal to 6 over 70. So the range of possible values of mu is greater than or equal to 6 over 70. And that there, ladies and gents, completes exam style question 1. Here is exam style question 2. So we've got a ramp AB of length 8 meter and mass 20 kg, which rests in equilibrium with the end A on rough horizontal ground. The ramp rests on a smooth cylindrical drum. The distance A to C is equal to 5 meter and tan theta is equal to 7 over 24. Find the magnitude of the resultant force acting on the ramp at A. Firstly, we're going to take the ramp AB to be a uniform rod. Now I'm going to label all the distances and all the forces acting in this particular diagram. For simplicity, we're going to consider the horizontal and vertical forces. Right, first of all, the weight of the ramp, we can label that at the center. So that weight is going to be 20 g. The weight 20 g is going to split the distance 8 meters into 2 equal parts. So 8 divided by 2 is 4. So this distance over here is 4 meter. We know that the distance A to C is 5 meter. So this remaining portion over here has to be 1 meter. So 5 meters used up, 8 take away 5 will give us 3 meter. So this distance over here is 3 meter. Now, over here, we've got a normal reaction and we can label it as RA. If this ramp was to slip, it will slip to the left and so friction will act to the right. Remember, the horizontal ground is rough, so there is friction. We can label that friction as FA. Because this particular ramp is resting on the cylindrical drum, there will be a normal reaction coming out and we can call that normal reaction RC. We can form a right angle triangle over here. Okay, we want to label all the horizontal and vertical forces. It can be shown that this angle is theta, the same as this one. We can put in the arrows. This component is the adjacent component, and so the force would be RC cos theta. This is the opposite component, so this force would be RC sin theta. Okay, so that is my complete diagram. Okay, now that we've got the distances and the forces labelled, let's proceed with the question. Find the magnitude of the resultant force acting on the ramp at A. So if we focus on A, we've got a normal reaction coming out, RA, and we've got friction acting to the right, FA. The resultant force will act in this direction. I can call it R. So we can construct a right angle triangle. This is my horizontal component, which is FA. This is my vertical component, which is RA. That resultant force can be written as a vector. So R as a vector would be FA I plus RA J. Our target is to calculate the magnitude of this resultant force at A. But to calculate this magnitude, we need to work out FA and RA. So what is FA equal to and what is RA equal to? FA is acting in the horizontal direction. So to work out FA, I'm going to resolve horizontally, taking right to be the positive direction. So horizontally, the resultant force F is equal to 0. So that would be FA minus RC sine theta. So FA is equal to RC sine theta. Okay, so that's good. RA acts in the vertical direction. So to work out RA, we need to resolve vertically. So resolve vertically, taking upwards to be the positive direction, the resultant force F is equal to 0. So if I resolve vertically, I've got RA minus 20G plus RC cos theta. This must equal 0. So RA is equal to 20G minus RC cos theta. Right. We can work out the exact values of sine theta and cos theta using the information tan theta is equal to 7 over 24. We need to construct a right angle triangle. So my right angle triangle, you can draw it here. So this over here is theta. Tan theta is equal to 7 over 24, opposite over adjacent. So 7 and 24. Right, so we can use Pythagoras' theorem to work out the hypotenuse, and that will just be 25. So from this triangle, we can work out sine theta. That will be opposite of a hypotenuse, so 7 over 25. And cos theta, which will be adjacent of a hypotenuse, 24 over 25. Okay, now, I've got sine theta, I've got cos theta. The only other obstacle is the RC, and to work out RC. So how do I work out RC? Well, if I go back to my conditions of equilibrium, I've used up this condition, resultant force horizontally or vertically 0. My other condition is the sum of clockwise moment is equal to the sum of anti-clockwise moment. So to work out RC, I'm going to be taking moment about the point A. If I do this, all the forces coming out of A are now neglected. So moment about A to find RC. So we know that the sum of clockwise moment is equal to the sum of anti-clockwise moment. Right, so if I hold my pen at the point A, I can see that this force over here will take the body clockwise, and this force over here will take the body anti-clockwise. Let's start off with the clockwise moment. So we've got the 20G force. I can stretch it out, okay, stretch it out and form a right angle triangle. This part here is theta. So the distance from A to that weight is 4 meters. This is my perpendicular distance to that force. So this over here would be 4 cos theta is the adjacent. Equal. Let's have a look at the anti-clockwise moment. We've got RC. The perpendicular distance from A to RC would just be 5 meters. Okay, that's my perpendicular distance. Now I'm going to calculate the moment of the 20G force and the RC force. So if I do this, I get the following. 20G multiplied by 4 cos theta. Remember, moment of a force is given by force multiplied by the perpendicular distance. This must equal 5 multiplied by RC. Hence RC is equal 20G multiplied by 4 cos theta all over 5. Okay, so I've got cos theta, it is 24 over 25. I can substitute that in. I know that G is equal to 9.8, the acceleration due to gravity. So putting this all into my calculator gives me RC. So RC is equal to 150.528 newtons. Okay, so that's RC. Now that I've got RC, I can substitute this value into FA and RA. And also substitute my sine theta, which is 7 over 25, and my cos theta, which is 24 over 25, and G equal to 9.8. So if I do this, I get the following result. Let's start off with FA. So FA is going to equal 42.14784 newtons. Okay, we've substituted our RC and we've substituted sine theta, which is 7 over 25. Now let's work out RA. So we need to substitute G equal 9.8 and cos theta equal to 24 over 25. So if I do this, I get RA is equal to 51.49312 newtons. Okay, so now we've got FA, we've got RA. We can go back and write our resultant vector in complete form. So our resultant vector is going to equal FAI, which is 42.14784I, plus RAJ, which is 51.49312J. Okay, so that's our complete resultant vector at the point A. Now we can calculate the magnitude of the vector. So the magnitude is given by square root I component squared, so 42.14784 squared, plus J component squared, 51.49312 squared. We can put this into our calculator to give us 66.54308 ... So ladies and gents, we can round off to 3 significant figures, and if we do this, we get 66.5 newtons to 3 significant figures. So the magnitude of the resultant force acting on the ramp at A would be 66.5 newtons to 3 significant figures. That there completes exam style question 2 and this teaching video on ramp and cylinder problems. If you found this teaching video useful, please don't forget to leave a comment, leave a like, turn on the notification bell so that you receive notifications every time I upload teaching videos. And please don't forget to subscribe.